In this video, I'm really going to try to kind of explain to you conceptually and mathematically this idea of hydronium and hydroxide concentration and equilibrium and how they're interrelated to each other and how they relate to Kw. I know some of you have a really good grasp of it, but I know some students are still struggling, so I'm hoping this video will help. So first, backing up a little bit, let's think about the Lewis structure of water. If I draw out the Lewis structure of water, it looks like this. Okay? It's got an oxygen in the middle with two lone pairs covalently bonded to different hydrogen atoms. I know the Arrhenius definition of acids and bases, the Bronsted-Lowry definition of acids and bases, and the Lewis definition of acids and bases. And all of them follow that water can be both an acid and a base, which is called apoprotic. Can behave as an acid and a base. Remember, your Arrhenius definition is that it produces hydronium in solution. So I do have to have two water molecules to do this. And we're going to do it through arrow pushing. Arrow pushing starts at a pair of electrons or a bonded pair. It starts at the electrons, so either lone pair or bonded pair. So this lone pair of electrons here on this oxygen comes over and steals this proton. There is currently this bond between the oxygen and the hydrogen holding it here. When the hydrogen leaves, it leaves behind its electron, so it leaves as a proton, and it leaves these electrons behind onto the oxygen. What's left after this process is this compound forms hydronium ion, and this compound forms hydroxide. And most students are pretty comfortable with that idea. There's a negative charge there, there's a positive charge here, we're looking for a formal charge. Students struggle a little bit with arrow pushing, but overall they're comfortable with this idea. So I have two water molecules that interact, forming hydronium and hydroxide. By the Arrhenius definition, an acid produces hydronium, a base produces hydroxide. So I'm following the most basic definition of acid and base, which is the Arrhenius definition. But I'm also following the other rules. A Bronsted-Lowry definition states that an acid is a proton donor. This donated the proton to the other species, and it forms a conjugate base. A base is a proton acceptor. This compound, this water molecule, accepted that proton, and this is the conjugate acid. So I'm following Bronsted-Lowry. I'm also following the Lewis definition. Lewis looks at electrons. An acid is electron pair acceptor. This accepted the electron pair when the proton was lost. It accepted that electron pair. A base is an electron pair donor. This compound donated a pair of electrons, or I guess I drew on the bottom here, donated this pair of electrons to form the bond. Okay, so just kind of connecting them all back to the definitions of each. So I am following the definitions of each species. But how does this relate to Kw? I didn't mean to erase those ones. How does this relate to Kw and this idea of hydronium and hydroxide being interrelated to each other? So if I don't draw this out this way, if I don't draw it out by Lewis structure, if I just draw it out by formula, it's a little bit less space consuming. I've got 2 water molecules, and I can either write it like this or I can just write them next to each other. It doesn't really matter. Whichever way you want to do it. But these form an equilibrium with 1 hydronium ion and 1 hydroxide ion. How do I know this? Experimentation. We have figured this out. So for ease, I'm going to use the top equation, but again, the bottom equation, they mean the same thing. The 2 in front, I can split it up into 2 different molecules here. But I just want my space back on my board. Okay, so let's go ahead and look at the K expression. Remember what K is. It's called the law of mass action. K is looking at how much product you have compared to how much reactant you have. So it's looking at the ratio. How far has your reaction progressed? K is also specifically at equilibrium. Q is when you don't know where you're at. You could be at equilibrium, you could be somewhere else, but K is specifically at equilibrium. So the water molecules have been allowed to react and they've reached equilibrium. The K here would be equal to the hydronium ion concentration times the hydroxide ion concentration. Remember, things in brackets like this mean molarity, so moles per liter. I look at the reactant side though, because remember, it's products over reactants, and I'm not going to put the reactant into this K expression. Here, water is my solvent, which means its concentration is staying virtually unchanged throughout this reaction. You may or not remember this, but we talked about this in class. Only about 1 in every 10 million water molecules undergoes this process. So the water concentration is actually staying virtually unchanged. So I don't put that into my K expression. But now I've got my K expression. We also know, because of studies, the value of K at 25 degrees C is equal to 1.00 times 10 negative 14. Again, just experimentation. We figured that out. We measured it. There is ways to measure hydronium and hydroxide concentration. For example, if you use a pH meter, pH, we know, tells us the negative log of hydronium concentration. It's a very helpful, useful tool. All a pH meter is what we call an ion selective electrode. pH meters are specifically counting how many hydronium ions they see in solution and then correlating it back to a mathematical function for us so that we can read it off a system. So I can actually measure the amount of hydronium in here. Excuse me. Again, this is at 25 degrees C. If I was at a different temperature, the value would be different. But the one we're going to use for class, unless otherwise noted, is 25 degrees C. We also know this is a special case of K, and we call it KW because it's the equilibrium expression specifically for water. So I know that both of these are, the product of these two, the concentration of these two is 1 times 10 negative 14. If I think about this though, that means that for every 2 water molecules, I produce 1 hydronium and 1 hydroxide. So if I actually set up a rice table there, this doesn't go into it. I assume I have none of this at the start. I assume I have none of this at the start. This is product, so plus x, so at equilibrium I have x and x. If I plug them into my K expression, that's the same as saying x times x equals 1.00 times 10 negative 14. X squared equals 1.00 10 to the minus 14. Therefore, x has to be equal to 1.00 times 10 negative 7, because I just took the square root of both sides. But remember what this means. This is equal to the hydronium concentration times the hydroxide concentration. So when these two are equal to each other, when I have the same concentration of each species, my KW is 1 times 10 negative 14, which I do have to memorize. But that means that I have 1 times 10 negative 7 of each species present. This is in neutral water. What do I mean by that? I mean that I don't have an excess of either one. Let's think about what this means conceptually. I have a beaker of water. And I put in some water molecules. And every so often, 2 water molecules, every 1 in 10,000, will react and form a hydronium and hydroxide. But it's in a 1-to-1 ratio. So at a neutral pH, meaning no excess of acid or base, just straight water, pure water, I have the same amount of hydronium as I do hydroxide. If I take the negative log of this, that's where I get the pH equals 7. Sig figs, there's 3 sig figs here. I need 3 decimal places here. The 7 in front is due to the log, and that's from this value up here, actually. So at neutral pH, meaning that I don't have an excess of either one, they're completely neutralizing each other, same amount of hydronium and hydroxide. Now, when I'm in an acidic condition, acidic means I've added something to the system that increased the hydronium concentration, but not the hydroxide concentration, okay? So I've added hydronium from an outside source. I've added HCl, I've added nitric acid, I've added any type of acid at all. It's going to add some protons to the system, making hydronium ions, okay? Whether it's a strong or weak acid, it's going to increase the hydronium concentration. But this always holds true. So that's what I mean by they're inversely proportional to each other. If I've got H3O plus and OH minus, and I add something to it to increase this concentration is going to go down. And if you think about Le Chatelier's principle, that should make sense to you guys. I'm going to try to move this out of the way. If I increase the concentration here, I've just increased the product side. What that's going to do, it increases here. These species are going to react, make some more water. It's going to decrease the concentration of hydroxide. If I instead add in something with more hydroxide, it's going to decrease this concentration. Same idea. I've increased the concentration of hydroxide. It's going to react with some of the hydronium and force the reaction the other direction, decreasing it. And so if I am at a pH of 7, the hydronium concentration equals hydroxide concentration. If I am at a pH less than 7, my hydronium concentration is greater than my hydroxide concentration. And if I am at a pH greater than 7, my hydronium concentration is less than my hydroxide concentration. But they are interrelated to each other. They're inversely proportional to each other because it's all based in water. Now, if you're not using water as your solvent, we're going to have something else going on here, but it's still the same basic principle behind it, okay? So in this class especially, we're looking at hydronium versus hydroxide and how that all interrelates. The other thing I want to say here, and I need to find some space here, so we're just going to erase this, is this idea of Kw. So I know I keep telling you that Kw is equal to hydronium concentration times hydroxide concentration, and that's equal to 1.0010 to the negative 14. But that is at 25 degrees C. Why do I keep emphasizing that? Because we know that that K expression is temperature dependent. Temperature is one thing that can change the equilibrium constant, okay? If I increase the temperature, it depends if it's an exo or endothermic reaction. If it's endothermic, heat is a reactant. Increasing the heat causes more product to form, makes Kw bigger. If it's exothermic, heat is a product. If I increase the heat, it makes the products react, makes more reactant, therefore my Kw decreases, okay? So if I had asked you, what's your Kw at, say, 45 degrees Celsius, but I gave you the concentration of either hydronium or hydroxide, you guys could easily figure it out. I honestly don't remember if this is endo or exothermic. It doesn't matter. I'd have to look at the values. But, instead of saying, I know at 25 degrees C, these are each equal to 1.00 times 10 negative 7. What if I told you at, 50 degrees, it was equal to 1.5 times 10 negative 7? I don't know. I actually have no idea what it is, but just something a little bit bigger. And I want to know the new KW value. If I have water, the two have to be equal. So whatever I tell you is the concentration for one is the concentration for the other, and then you just multiply them, find the product to find your KW. I hope that helps clarify a little bit more of this idea of KW. One more thing I want to mention about this KWK thing is that I want you to think about Ka and Kb. They are interrelated with KW. So we have an equation, KW equals Ka times Kb. This is really useful when you're trying to find the Ka or the Kb for some species, but you have the opposite value you need. And so again, KW is equal to 1.00 10 to the minus 14 at 25 degrees C. But how does this come about? How does this equation come about? Well, let's think about a weak acid. A weak acid is HA, okay? And this is just a weak monoprotic acid. If I put this in water, it forms an equilibrium with A minus, which is the conjugate base, and hydronium ion, which is the conjugate acid. So again, just bringing those terms back, acid, base, conjugate acid. If I wrote the K expression for this, my K expression would be a Ka because it's an acid dissociation, and Ka is equal to the concentration of the conjugate base times hydronium concentration divided by the concentration of that acid. Again, I'm not including this water here. It is acting as a base, yes, but I'm not including it because it's at the liquid phase. It's my solvent, which means that the concentration is virtually unchanged for the amount that's actually dissociating or reacting here. So I know I've got my Ka. Let's move that over a little bit for some space. Let's think about the same thing with B. If I have a base in solution, I'm going to use the conjugate base and how that would react in solution. So I just said A minus is the conjugate base, meaning that it's the base that forms after that weak acid loses its proton. A minus will also react with water, but in this case, because it's a base, it's going to accept that proton, forming HA and hydroxide. So again, the A minus stole the proton, forming an acid, and conjugate base. Again, water acting as that amphiprotic species, acid or a base. The K expression here would be a Kb because it's a base doing it. And how do I clarify besides just that I know it's acting as a base? Because it's forming hydroxide. And again, if I've got hydronium in my numerator, that's Ka. If I've got hydroxide in my numerator, that's Kb. This will be over A minus, which is that base. It's the conjugate base, but in this system, it's acting just as the base, right? Because we're putting on the reactant side. So reactants are acids, bases. Product side is conjugate acid or conjugate base. Now, what if I multiply these two together, though? If I multiply Ka times Kb, and I'm saying that because I'm telling you up here, I'm multiplying them together, right? This would be the same. Well, let's just move them. This times this. Cancel things out if they're in the numerator and the denominator. So let's find a color that we can see a little better here. HA and HA, A minus and A minus, and what's left over? H3O plus times hydroxide ion concentration is what's left over. which equals Kw. So when I need to know my Ka or my Kb, and I have the other one, I can go through Kw. I can give you one of many things to be able to solve questions with weak acids, weak bases, conjugate acid, or conjugate base that are weaks. I can give you Ka. I can give you Kb. I can give you pKa. I can give you pKb. Remember, pKa is the negative log of Ka. pKb is the negative log of Kb, because all that p means is negative log. So to get to Ka, 10 to the negative pKa gives me my Ka value. To get to Kb, 10 to the negative of my pKb value gets me to my Kb. And then, of course, Ka times Kb equals Kw, which is 1.0010 to the negative 14 at 25 degrees C. Hope this helps clarify some of it and see some of the conversions that you're going to see in a lot of the practice.